And it was noted in the reading questions, you can read the statement of the theorem, although that's not going to be terribly important, that there's a line in here. It says it should not be too difficult to see why a sub n goes to x, where what they found is that a sub n belongs to this 1 over n neighborhood of x intersect a, where a sub n is not equal to x. So the reading question was, they say it should not be too difficult to see, but it might be kind of difficult to see. So in this screencast, I'm going to point out kind of what's going on here. So read the proof, read the theorem if you like, but you can get a lot out of this by just listening here. So first what I want to do is I want to draw a picture of what's going on here. So I'm going to draw a number line. Just make the line a little bit thinner perhaps. So here's a picture, not a very good one. Here's x. V of 1 over nx it's a 1 over n neighborhood, where you can think of epsilon as 1 over n. What that means is that I can go over here, x plus 1 over n, go over here, x minus 1 over n, and I just look at the open interval. So what this is saying is that this is just equal to the open interval x minus 1 over n, x plus 1 over n. Other people commented that the notation is difficult. I agree, but this is how you translate it. So in other words, an a sub n is in this interval and also in a. So maybe a sub n is in here because it has to be within the interval, and also I know that's in a. So those two facts tell me a lot about the a sub n. So I'm skipping over the point how they found these a sub n because that wasn't the question. But once you have these a sub n, what you can do, and maybe it's worth pointing out that that's for a fixed n. I don't want that color. I want it to be black. So I'm just going to draw over it because I'm too lazy to erase it. You might forgive me. If not, I don't need you anyway. Okay, so 1 over n, great. But what they also do then is for 1 over n plus 1, they get another epsilon neighborhood, x minus 1 over n plus 1, right? Because n can be anything. It doesn't just have to be a single thing. They're creating an infinite number of these. And then they get another a sub n plus 1 that's in there. So they're getting an infinite number of these. And so that creates a sequence. And then why does it converge to x? Well, what do we need? We need, I'll go back to my writing. We need, for all epsilon bigger than 0, there exists an n such that, what do we need? A sub n minus x is less than epsilon for all n bigger than or equal to capital N. Okay, I'm going to show you how this up here gives us this. So the way I'm going to do that is I'm going to prove it right here. And the way we start almost every proof is we fix an epsilon. Let epsilon be bigger than 0. And then what I'm going to do is I'm going to by the Archimedean principle, there exists, let's call it, I don't know, let's call it an n naught, that's a natural number, such that 1 over n naught is less than epsilon. Why do I say that? Because epsilon's positive. Then what do I get? Right? Then my picture is going to give me, I'm just going to draw a quick sketch right here. Here's my x. Here's my x plus 1 over n naught. X minus 1 over n naught. And then what that means is that I have some a sub n naught there. So what that tells me is that the distance between a sub n naught minus x is less than 1 over n naught, which is less than epsilon. So that means it converges. So all I need to do is let n equal that n naught, and then it's going to work. And that's how it goes.